Okay, so let's go ahead and get started. So I'm really delighted to have Elizabeth DuPre give this talk. I was joking with Elizabeth that we take credit at Neurohackademy for everything that she does in her career, because she came to the very first, it was 1 week at the time. I guess it's 1 week now. It was Neurohack Week, but she came and it was fantastic to have her. And we had her come last year and did a tutorial, and that was fantastic. And I think at this point, if we could have her do everything, we would, but she refuses for some reason. So we at least have her doing Nilearn today, and I'll just let her take it away.
Great, thanks so much, Tal. Yes, it's really lovely to have been able to come back to Neurohackademy a couple of times now. I really just, I think I said this yesterday, but I can't say it enough. Like, the community here is really, really great, and kind of having a chance to meet people and just to talk about these ideas is really fantastic. So I'm so glad you could come check out Nilearn and we could talk a little bit about it. Okay, so let me quickly share my screen. Perfect. Okay.
Yeah, I can see it.
Nice. So I'm going to have two windows open. One is the Jupyter Lab for the course, or for the Neurohackademy as a whole. And the other is going to be this link that I've pasted in the Slack channel. So if you go to emdupre.github.io/NHA for Neurohackademy 2020-Nilearn, that's going to take you right here. And so this is just a Jupyter book. Basically what it is it's just a rendered version.
Could you, sorry, Elizabeth, yeah, could you maybe just expand that tab, just because I'm not sure people can see all of it. So just,
yes.
Or
I'll just,
yeah, just put it in the chat, actually.
Chat.
That's probably,
yeah.
Actually, I'll do that. You can keep talking.
Okay, either way, it's also in the Slack. But yeah, so basically what this is it's a Jupyter book, which just means that I've taken the IPython notebooks and I've rendered them as a website. So in the curriculum for this lesson for Wednesday Nilearn, you also have access to the same Jupyter notebooks, but I just find it's nice to have kind of the rendering open so we can really see the code and the ideas in one place, and then we can execute them side by side. I find that makes it a little bit easier to think back and forth between the two. Okay, perfect. So I'll be monitoring the Q&A throughout. If you have any questions, feel free to just add one in. So in this tutorial, we're going to talk about the Python library Nilearn. And the goal is to really show how Nilearn allows us to easily perform machine learning analyses with neuroimaging data, specifically with MRI data and fMRI data. So yesterday, you may have been to Tal's Intro to Machine Learning Analysis, where he used the library sklearn or scikit-learn. And you may notice right away that the name Nilearn sounds awfully reminiscent of scikit-learn. And this isn't an accident, right? So Nilearn and scikit-learn were actually created by the same team in Paris. And Nilearn is designed to bring machine learning to the neuroimaging domain. That's where the name really comes from. So with that in mind, let's first really think about why we might want specialized tools for working with neuroimaging data and doing machine learning analyses. So typically, when we perform a machine learning analysis, our data often looks something like this. And I'm just going to copy this into the notebook, and hopefully you can follow along as well and do that. I find it just helps to think about it a little bit more. So if I import pandas, I can do data equals pd.read CSV. And in this case, because I'm on the Jupyter Hub, I'm going to do this tilde for home, Nilearn underscore data / abide 2.tsv, separator equals tab, and then data, I'm just going to show the first few rows. So if you do that, you should get something just like you see in this notebook, which is to say that we see, it's clearly in a table format. We've got some different rows. We've got a bunch of different features that might be of interest, like site and subject and age. And actually, if you went to Tal's tutorial yesterday on Introduction to Machine Learning, you may recognize this data set, right? This is exactly the same data set he used to show how to do some machine learning analyses with the Abide data set. So Tal already went through a lot of really cool things you can do with this data set, but for our purposes, I want to step back for just a second and think about the structure of this data set. So the data is already structured in a tabular format with pre-extracted features of interest. So this makes it much easier to think about some of the things Tal discussed yesterday, like what features would we like to predict, or how should we handle cross-validation. But if we're starting with just the neuroimaging data, how can we get to a representation like this, right? So this already has, you know, some of the demographic data, this makes sense, but we have all these ROIs with values in them. How can we get something like that from just neuroimaging data? And if you haven't, let's say, looked at neuroimaging data before, I just want to talk a little bit about why this might be a challenge. So one thing is that neuroimaging data definitely does not have a tabular structure, right? So it has both spatial and temporal dependencies between successive data points. That means that knowing where and when something happened tells you information about what's happening in the surrounding data points. We also know that neuroimaging data contains a lot of noise that's not bold related, such as head motion. And so since we think that bold related signals are related to neural firing and are therefore of interest, we often want to consider how we can make sure that our analyses are not driven by these non-bold related signals like head motion. And this all seems, you know, like reasonable. And there are lots of neuroimaging software that can deal with these kinds of concerns. But most machine learning software libraries are not designed to deal with this at all, right? How could scikit-learn deal with head motion, for example? What would that look like? So rather than thinking about how we can get these things into, you know, a software like scikit-learn, Nilearn provides a way to deal with these directly while interfacing between the two and makes it really smooth and seamless. So first, let's just look at some data. That always helps. It's a great place to start to get a sense of a problem. So you may have your own data locally you'd like to work with, but Nilearn is also quite nice in that it provides access to several neuroimaging data sets and atlases. And we'll talk a little bit about atlases later, but just to know that you can grab both kinds of data directly from Nilearn. I also want to shout out that all of these are only accessible because research groups chose to make their collected data publicly available. And that's, you may have noticed a theme in Neurohackademy. Publicly available data is just a wonderful, wonderful resource for everyone. And so we definitely owe them a huge thank you for this. So in particular, the data set we're going to use today was originally collected by Rebecca Sachs's group at MIT, and it's hosted on OpenNeural. So we at the Nilearn team pre-processed the data set with fMRI prep, which Oscar is probably talking about right now in his NIPREPS lecture, and downsampled it to a low resolution so it'd be a little easier to work with. So you can go look at the Nilearn documentation to learn a lot about this data set. In particular, you can see things like this data set contains over 150 children and adults who are watching a short Pixar film. So we don't want to work with all 150 participants. That's a bit too much just for the purposes of illustration. So let's just go ahead and download the first 30. So Nilearn makes this really easy. You can do it in just one line. So what I'm going to do is I'm going to say from Nilearn import datasets, development dataset equals datasets.fetch development fMRI. And then if I just executed this command, it would pull down all 155. So instead, I'm going to say the number of participants I want is 30. Oops, 30. And then if you're running this in the Jupyter Hub, which I'd really recommend, it should be instantaneous because I've actually already gotten this data for you and it's already stored in the hub. If you're running it locally, it'll take a little bit longer and that it'll go ahead and cycle through and fetch all of those different data points for you. Okay, so now we have this development dataset object that we've just created, and it has several different attributes which provide access to almost all, really, I think, the relevant information we would need in processing this data set. So for example, development dataset phenotypic provides information to know whether or not participants were children or adults at the time of the scan. We can also access directly the functional MRI data using the .func attribute. And if you were just in Chris Markovich's NIBABL lecture, you may have learned a little bit about that library already and seen that we can use it right away just to learn a few things about this functional data, including the shape. So that is how many time points were collected. and other information about it. So first, let's just go ahead and do that for the first participant. So if we do import nibabble as nib, image equals nib.load, and then we're just going to call the development data set that we just created, func, and then I'm going to pass the 0 index to mean for the first participant. And then I can do image.shape. Import nibabble as nib. There we go. Okay, perfect. So we can see just as here that it has, each volume has a 3D shape of 50, 59, 50, and there are 168 time points for this first participant. Okay, so I told you we'd view the data, and this is one view on the data, but what if we wanted to like view a 3D image of the data, right? Now that we know a little bit about it, let's actually look at it. So this is something, if you're in the Nibabble lecture, you may have seen that Nibabble has several tools to do this, including OrthoView, but Nilearn also includes lots and lots of plotting functionality. This is one of the things I really love the library for, because it has so many different ways to display and look at your data. So in this example, we're going to use the view image viewer because it's going to launch something interactive for us. We're also going to use a way that Nilearn provides to subset or index the full time series. So again, we have 168 volumes, but if I want to interactively click through a single volume, I don't want to pass all 168, right? That would be 168 viewers. So instead, I'm going to use this image.meanImage, which is going to take the mean over time. So the mean over all 168 volumes, and I'll just have one 3D spatial image that I can then click through. So let's just go ahead and do this, right? I'm going to hide the viewer because it's pretty cool. All right, import matplotlib.pyplot as plt. And then I'm just going to do 2 different Nilearn imports. So from Nilearn, import image, and from Nilearn, import plotting. Then I'm going to, just as I described, take the mean image. So using this Nilearn import, I'm going to call mean image, and again, just take it for the first participant. And then I'm going to then plot with view image that mean image. And because I just want to look at it, I don't want to threshold it in any way, I'm just going to say threshold equals none. And it's going to think a second. Here we go. Okay, so now what you should be able to see is you have a viewer that launches directly in your Jupyter lab or in your notebook, where you can actually click through the image and look at it yourself. This is really, really nice. This is something that is just always good to do with your data, just to look and see what it looks like, and having it in this interactive format is really helpful for being able to do that quickly. So Nilearn is geared towards these sorts of things. All right. So this is pretty cool. We like how this looks, but I promised you that we would be getting towards machine learning analysis, right? And what we started with was this table with all these pre-extracted features from different ROIs. And this doesn't really help us there. This shows us what it looks like, but it doesn't help us get to this tabular representation. So how can we get there? What do we need to do? What we'd like to do, really, to step back, is to extract and transform meaningful features from the data and store it in a format that we can easily work with. So we could work with the full time series directly, right? We could just go ahead and look across all the voxels, but we often want to reduce the dimensionality of our data in a structured way. This is really pretty common if you think about things like parcellations. So we may only want to consider signal within certain learned or predefined regions of interest, and when taking into account known sources of noise, so like that head motion example I gave earlier. So luckily, Nilearn provides a really easy way to do this as well, which is this class of objects known as the masker objects. And before I talk a little bit about masker objects, I just want to jump back. So there's a question, which is, what is the threshold for? Back here on this plotted view image. Great question. So what is the threshold for? This is just if you had an image and you wanted to interactively explore it, but you wanted to provide a threshold on it so that you didn't see any, values in the image below or above a certain number, then you could pass threshold there. So it has a default that is pretty sensible, but in this case, I just wanted to show the whole image. So I said threshold is none. But that's a great question. Cool. Okay, yeah, and please feel free to add in other questions as we go. All right, so we want to figure out how we can extract structured features and control for these things that we think are of no interest. So the masker objects help us do this. And just to get a sense of what masker objects are doing, let's first think about what masking fMRI data really looks like, right? So if you have a 3D volume or only one time point, you can imagine it looks something like this, where your whole fMRI volume or MRI volume is a cube, and you have this mask that you've drawn or someone else has drawn or is created through some other way, and you only are interested in values, particularly in there. But if you have a 4D time series, this doesn't quite work because each volume is now its own 3D cube. So what we need to do is over time apply the same mask to each of the volumes. And at the end, what we'd really like to see is a 2D array that tells us, here are all the different voxels that were within the mask, and here is what they looked like over all of these different cubes, in our case 168. So the mask is telling us which cubes or voxels we'd really like to sample from, and by providing this mask to a 4D image, we'd like it to be smart and actually apply it over each of the 3D frames, right? So masker objects are designed to allow us to do exactly this. So first things first, we need to define a mask or several masks that we'd like to apply. This, as I said, this may make you think of parcellations, and just like that, this could correspond to one or many regions of interest. I'll also note here, although I won't talk about it because I think Pierre Balek is going to talk about it a little bit more tomorrow, Nilearn does provide methods to define your own functional parcellation. So you could learn parcellations using something like k-means on your own data using Nilearn. But for now, let's just say that you want to use a parcellation or a mask that someone else has defined. Nilearn provides access to lots of those that are pretty common in the literature and widely used in the field. So it makes them much more accessible for working with our own data. So in this tutorial, we're going to go ahead and use one that is pre-computed and available in Nilearn called multi-subject dictionary learning. If you're interested, I'd really encourage you to check out this paper. And the important thing here is it's going to define a set of probabilistic regions of interest across the brain. And so what we can do is we can just go ahead and directly import this atlas using Nilearn. So we'll do import numpy as np. And then I'm just going to abbreviate it MSDL. Fetch atlas MSDL. And then just as before, when we fetched the development data set and it had all these attributes, this MSDL, this atlas, also has some really useful attributes that we can take advantage of. So one is the region coordinates. That just tells us where the different ROIs are located. So that's really quite useful. So I'm going to save it out to its own attribute. And then I can use that to figure out how many regions there actually are. So I can say the number of regions is equal to the length of MSDL chords. And then just to make it really easy, because it's always nice just to have confirmation, we're going to go ahead and print to screen exactly what we found. So MSDL has this many regions, part of the following networks. And then what this is going to do is it's just going to insert a line break. And then we're going to do NumPy, which we've already imported. We're going to say, what are the unique values in this other attribute called networks. So that gives us for every region of interest, what network do we think it belongs to? And then I'm going to do end the string and the print statement and execute that. Nice, okay. And you might see something like this. So again, if you're not running this on the Jupyter Hub, it would need to download the MSDL Atlas. Because I've already downloaded it, it should go really quickly for you. And then you can see that MSDL has 39 ROIs. Each are part of the following networks. And you can just see the networks listed here. These may be things that you're familiar with if you're working with neuroimaging data somewhat, like auditory networks or language networks, motor networks. So this is really nice. This provides us a lot of information right out the bat, right out of the gate. So maybe, you know, just to say, maybe MSDL isn't your favorite atlas. There are lots and lots of others that Nilearn ships with, including the Schaefer Atlas or the Harvard-Oxford Atlas. The important thing is that you know what atlas is best for your research question. But here, as I said, we're just going to stick with MSDL. I think it's quite nice. So it's up to you. One thing that's also nice is, as I told you before, Nilearn is really, really great about plotting. So we've already seen how we can plot an image interactively. There are also really nice ways to plot our atlases. So because I told you MSDL is a probabilistic atlas, we can view it using this plot prob for probabilistic atlas command, nicely named. So let's just go ahead and do that and see that we get the same results. And you should see something like this, right? So what this is just kind of the standard MNI 152 brain overlaid with different colors marking the different regions of interest that are defined in this atlas. And again, you could do this for whatever your favorite atlas of interest is. Just, you know, making sure that if it's probabilistic, you'd want to do probabilistic. Okay, there's one quick question. The best way to load a parcellation from masking that is not available in Nilearn, if you have the nifty file or .label file, for example. Yeah, that's a great question. Okay, so the question is basically, let's say that I have an atlas and I'd really like to work with it, but it's not yet, or you know, maybe it won't be for whatever reason available in Nilearn. How can I actually work with it? This is a great question. So it depends in large part on what kind of atlas it is. So, you know, if you have a surface atlas versus if you have a volumetric atlas, they have slightly different attributes that you need to worry about. The main thing is you want to provide an index of basically how these map onto different features of interest. So if you want to treat it as just various masks, all you would need to do is kind of have the masks in the format, and then you could directly supply it to something like plotprobatlas. If you have a .label file, that makes me think that you're using something like a Gifty, and there it would be a little bit more involved. I'm happy to talk about that afterwards. But if you just have kind of an atlas kind of like the Harvard-Oxford Atlas or like the MSDL Atlas, but it's not in Nilearn, you could really treat it similarly. It just wouldn't have those extra pieces of information, like what networks does it correspond to. That's something, though, you could add in yourself. No, that's a great question. Okay, next question. Can you plot a probabilistic atlas in an interactive format similar to the above? That's a great question, too. I actually don't know off the top of my head. Yeah, I'm not sure. We've recently been working to add more interactive viewers. That's something Jérôme Ducas in particular on the development team has pushed really hard on. So if it's not yet possible, it's definitely something that could be possible. But this is something where I would say checking out the documentation, because that's probably the most up-to-date place, would be best able to tell you, can you do that yet? But yeah, that's definitely something that I think would be of interest if it's not yet possible. Okay, perfect. So let's say for the sake of argument, that you have this atlas defined, and let's say that you want to use the one that's already in Nilearn, or that you've gotten one that you're working with locally and you've loaded it such that it can work with, or it's accessible to Nilearn. So what are we going to do, right? What's next? So I've been telling you what we need is this masker object, and the masker object is going to allow us to take our time series and apply the masks that are present in our atlases, and extract values therein that we can use for machine learning. But I do want to point out that maskers are more than one object, right? I call them the nifty masker zoo here, because there are a number of different kinds, and it really depends on what kind of mask you're trying to apply. So the canonical one is just called nifty masker. And this works really, really well if you have a single mask that you want to apply to the data. For example, like a brain mask, or if you just have one region of interest you're trying to extract. This is kind of the one that you usually want to use. But if you actually have several ROIs, as in our case, you'd want to use a slightly different nifty masker. So if you have maybe traditional, hard, or deterministic parcellations, then you'd want to use Nilearn input data nifty labels masker, because that will allow you to get all the different parcels. But because we're working with soft or probabilistic regions of interest, we can instead supply these regions of interest to nifty maps masker. And that's what we're going to be using here. But again, this is a recurrent theme. If you want to see the full list of available masker objects, see the Nilearn documentation. So I think Tal said this yesterday in his lecture, that scikit-learn is really held up as kind of this canonical example of the power of documentation. I would absolutely agree with that. And I would say that you can tell that Nilearn is from the same development team, and that the documentation is really, really lovely and really top-notch. So if you have any questions about that, I would definitely start by looking there, including just to learn what are the other kinds in the nifty masker zoo. Okay, so there's a question which is a masker necessary? Wouldn't the whole image provide more information for machine learning? So this is a great question. And basically, this has to go back to something, it's partially that Tal said in his lecture the other day, and partially just related to the idea that we want structured signal, right? So a couple of things. One is that if you reduce the dimensionality of the signal in a smart way, you can actually be more efficient and more likely to reach convergence for various machine learning algorithms, which can allow you to more efficiently learn. So oftentimes it's really useful to reduce dimensionality. The other thing is that many people have thought about this question specifically for neuroimaging data and come up with many different parcellations, for example, which may reduce the dimensionality in a very structured way that still preserves the signal quite well. We're also going to see that, if you'll remember, I mentioned that for neuroimaging data, we have this other unique set of concerns, which is that there are some sources of noise, right, that at least we think that they're noise, which would be things like, I'm just going to come back to it, head motion. And we want to make sure that those are not included in our, or at least we minimize the effect of those in our model. How about I'll say that? Because we think that we don't want to learn differences based on those features. We want to learn differences based on neural features. And there's good evidence to suggest that these are not related to bold and therefore not neural. So you often do want to provide a masker object both to reduce the dimensionality and to handle some of these other concerns. But it's a great question. It will also depend in part on what you want to do, right? So Nilearn, scikit-learn, for example, doesn't do convolutional neural networks. So we don't worry about interfacing with that here in Nilearn. But if you wanted to do something like that, you need to think about a slightly different set of corrections. Great question. Okay. So as I mentioned, because we have this MSDL atlas and because it has these probabilistic regions of interest, what we'd like to do is supply these probabilistic regions of interest to nifty maps masker. So how are we going to do that? First, we're just going to go ahead and import this module input data, which is where all the different masker objects live. And then we're going to just say masker equals And we're going to say, just as we mentioned, nifty maps masker, MSDL atlas, and we're going to use the maps attribute. And then I'm going to pass a few different parameters, which are really, really useful. So I'm going to give it a resampling strategy. So, oops, resampling target, which is useful if you're working with different data to make sure that they all have the same dimensions, which you may, if you went to Chris Markovich's lecture on NIBEBL, you'll know is quite important. So I'm going to pass the TR that we know from the data documentation, because that's going to be really useful for my low pass and high pass. I'm going to ask that we detrend the signal. And then I'm going to give a low pass filter and a high pass filter. I'm going to call this .fit. Okay, so there's a quick question, which is the main difference between nifty maps masker and nifty labels masker if the ROIs are not overlapping or not? Right, exactly. So the difference is if you're working with a probabilistic or a deterministic atlas. Great question. And so yeah, we walked through this a little bit here, but again, if you click, so I'm going to go ahead and click over. And it's going to take a little while. Okay, my internet is apparently too slow for this. But if your internet is better than mine, you should see that it takes you directly, here we go, to the part of the documentation where it lays out all the different nifty masker types, and you can go ahead and click on them and they'll give you even more information. But that's the main kind of difference I would highlight. Yes, great question. Okay, cool. So coming back to our instance of nifty maps masker, what we have is, again, we're passing in the actual maps that belong to the atlas. These are just telling you the different regions of interest. We're going to go ahead and do a few other parameters that are really very useful for working with this kind of data. So one I see a question on is detrending. So that's just basically z-scoring it over time. Oh no. Let's see how that worked. Hold on, I just don't know if I lost my internet. No, okay, it worked. Don't know what that was about. Okay, so sorry, so z-scoring it over time. And then you can do this low and high pass, which is kind of the band of frequency values through which you want to allow signals to pass. One thing that you may notice from the code of this code, if you went to Tal's machine learning tutorial, or if you've already used scikit-learn, is that we're calling this .fit method. And this may look familiar if you've seen scikit-learn estimators before. And what may be confusing about this in that case is that we're not actually passing any data to it. So if you've worked with scikit-learn estimators, you may be like, why are we calling it .fit, but we're not fitting it on any data? That's a great question. Just to kind of show here, the difference is really that we're fitting on these provided ROIs, right? So we're just saying that these are the ROIs that we want to use. And this is what we're going to then use to transform data that we supply to it, this ROI and these particular parameters. So that often I find trips people up in the beginning, but that's just a good thing to know. Okay. Yes, perfect. And then there's a question about working with structural MRI data. So I'll get to that a little bit later, but that's a great question. Cool. All right, so now that we have this masker object, let's just use it, right? This is supposed to be easy, so let's see if we can just use it to transform our data. So we can go ahead, let's just call it ROI time series, because there's nothing wrong with long variable names. Masker.transform, development, data set, and then I'm going to call fMRI, and again, I'm just going to pass 0 because I only want the first participant here. And then I'm just going to ask, what is the shape? And as you can see, it's 168 by 39. So this seems fine, but if you remember, the original dimensions were 50, 59, 50 by 168, and now it has a shape of 168 by 39. So those don't quite match, right? What happened? So what happened is that a couple of things happened. One is that because we had these 39 regions of interest, as we've talked about already, we don't really want to consider the entire brain anymore. We now want to consider just these 39 regions of interest, and we can therefore kind of aggregate signal within those regions of interest, which explains why we went from 50, 59, 50 to 39, right? So why we went from the original 3D shape to only having 39. The other thing is that now the 168, which used to be the last dimension, is the first dimension. So you could say the dimensions flipped, or we just transposed the matrix. And that's a little confusing if you haven't seen this before, but the reason is this is just the scikit-learn convention. So traditionally in scikit-learn, you think about it that rows in a data matrix are samples, just like we had before in the first data set that I showed you that Tal had used. And then columns in the data matrix are features. So if we had it the other way, it would actually have flipped these two, and it would have made it much harder to work with things like scikit-learn estimators a little bit later on. So Nilearn is quite clever for you and goes ahead and makes sure that things are in the right dimension, such that when you look at the matrix, you'll see that the time points are samples and the different regions of interest are your features. And again, this is really, really nice because if you're trying to do this yourself, you want to make sure that you don't accidentally flip these, because then when you go to use the scikit-learn model, you would have very different results maybe than what you expect, because you're doing a slightly different thing. Perfect. Okay, someone's preempting my question about fMRI prep, so we'll get there. Don't worry, we'll get there about fMRI prep. Okay. So the next thing we want to do is you say, great, okay, I have these 39 regions of interest, and I have for each of the 168 time points, but what am I going to do with that, right? What does that mean? And I see we're a little short on time, so instead of just copying out the code or writing out the code, I'm just going to copy it in. So Nilearn is really nice in that it knows that functional connectivity is something that we in the field often are really interested in and want to be able to do. So it has this whole class called connectivity measure, and that's going to make it really, really easy to generate functional connectivity matrices. So the first thing we're going to do is we're just going to say the kind of connectivity measure we want is correlation. There are other kinds, and we'll get to that after the break. But what we're going to do is we're going to then take this connectivity measure, this correlation connectivity measure, and we're going to use fit transform on this ROI time series that we just created with our nifty maps masker. And then we're just going to see what it tells us. So perfect. Okay, so it executed fine. And now what this correlation matrix is a functional connectivity correlation matrix. So you can go ahead and confirm that just by plotting it. And so here what I'm doing is I'm just filling the diagonal with zeros, so it's not one, it's a little easier to interpret or look at least. And then I'm passing the correlation matrix, and I'm going to label it with another attribute that came populated in the atlas, which is the labels, telling you what each region is. It's going to have a little warning, and then you can see we already have a functional connectivity matrix. So this is really nice. This is a pretty seamless way to get a matrix right away, and you can look at it and see a pretty clear block structure, which may be familiar if you've worked with this kind of data before. The other thing is I told you that Nilearn has lots and lots of ways of plotting. So rather than just looking at a matrix, you can actually even view it as an interactive connectome. So this is powered by Plotly, and it's something Jerome, again, worked on getting in, and it's really beautiful. So now instead of just seeing this as a matrix, it's going to take a second. Here we go. Now we have an actual brain that we can see all the connections embedded on. And you can move it. You can see there's quite a lot here, right? Like it looks like there's a lot of connectivity happening. Sometimes it's easier, yeah, like this. But this is really cool. This is a really nice way just to explore the data and to see kind of what the functional connectivity looks like. All right, so I told you in the beginning that something else that's really important that most machine learning models don't consider is how we can deal with these sources of noise. So for example, head motion, if you've worked with fMRI prep before, which again, Oscar's probably talking about right now in the NIPREPS lecture, what you can know is that when it does pre-processing, it generates quite a few different kinds of what we'll call confounds for you. And so because this data set was pre-processed with fMRI prep, we also have access to all of those confounds here. So we can actually use the .confounds attribute from development dataset, and we can see what these look like. So you'll notice that here you can see we have different kinds of motion. We also have this frame-wise displacement summary measure, anatomical comp core. We have the first 5 components, and then some CSF and white matter measures. So if you've worked with fMRI prep, you may notice this is actually a sub-selection of all of the available confounds. This was a choice we made when we added the data set, that we just wanted to go ahead and sub-select some confounds that are quite popular and therefore would be useful. But if you really want to access the full list of confounds and subset it on your own, when you originally fetch the data, you would just say reduce confounds equals false. And then that would provide you with all of the confounds fMRI prep originally generated, and you could sub-select which ones you'd like to use. Okay, what's really cool is that because we have this list of confounds, we can actually pass these directly to our nifty masker object. So I'm just going to copy this in. And then what you can see is, so now I have this corrected ROI time series, which is exactly like the ROI time series before. The only difference is that I'm supplying to the masker, this confounds parameter, and I'm setting it equal to the confounds for the first participant. And then just as before, again, I can take that same correlation measure, that connectivity measure where kind equals correlation, and fit transform this time series, and then I can plot the resulting corrected correlation matrix. And what you can see is already, it looks quite different, right? So if this is what, this is what our original one looked like when we weren't correcting for confounds. This is now what it looks like when we are correcting for confounds. And if you just want another layer of confirmation that it's important to correct for confounds, we can go ahead and copy in the same view connectome, the interactive one, now using this corrected correlation matrix. And what you'll see in just a second, here you go. What you'll see is that now we also have a slightly reduced connectivity connectome, rather, I should say, compared to what we had before, which was, had a lot more connections. So it seems like what's happening is that when we correct for this confound or this known source of noise, we're getting different results. And this is just a really, really good reminder about how important it is to try and correct for these data sources before you go into your machine learning analyses, so that you're not accidentally learning on these features of no interest, and instead you're learning on features that you're interested in and care about. Okay, so that's what I wanted to do before the break, which should be about now, but we can take 1 or 2 questions and then we'll start the break. How about? Okay, maybe I'll start from the bottom. So one is, because we're adding, I assume, confounds, because we're adding confounds to the masker already made, it will still do filtering as defined in the first masker, right? Yes, exactly. So here we can kind of see exactly what's happening if we look at the different steps. So here we're defining this masker, right? And we're saying, this is my nifty maps masker. Here are all the different arguments I want it to have. But then when I go to call it, in this case, I just call it without confounds, but later on I call it with confounds. In either case, what it's doing is it's just taking the existing master objects and it's transforming the data that we supply to it. So I don't need to restate, you know, exactly the ROIs I want to use or all these other parameters of interest. I can just supply the data and it will know to do all of this. And, you know, in the case of the second call, also to correct for the confounds. But yeah, that's a great question. We're just, we're keeping all of this and now we're adding in confounds. Great question.
You're getting a lot of questions, Elizabeth. You're welcome to answer them. If you'd like, I can also try and take a pass at ones if you want to keep going. Steve.
Yeah, I was going to say, I think we're pretty much at a break time. So I'm happy to either take one or two more or just go ahead and break and then answer them as we go. Maybe the last one. Okay, so I'll take last one really quickly because this is important too. All of these charts are just connectivity of one subject. Yes, exactly. So when we come back after the break, we're going to talk about, you know, when you do a machine learning analysis, usually you want to look across subjects. That's exactly what we're going to do after the break. But it's much easier to see all of this on one subject, so you can just see what's happening in full. And then now that we have kind of an understanding of all of this, we can apply it across multiple subjects and worry about doing a classification. Actually, we're going to classify whether participants were children or adult when they got scanned. Perfect. Okay, and with that, maybe we'll take a 10-minute break and then come back. Perfect. Okay, so we'll take a 10-minute break. We'll come back 5 minutes, 6 minutes to the hour, and then I'll try and work through a few more of these questions. Thanks. Okay, I think we can go ahead and get restarted. It's 3 minutes to the hour, so a little more than a 10-minute break, but not much. I know this is a lot of material, so we're just going to go through it because I think the really nice thing is just to see how we can really get from our neuroimaging data all the way to an analysis, right? A machine learning analysis like you may have seen in Tal's tutorial yesterday, or you'll see a few more examples in Gael's tutorial tomorrow. But this is just to show you how we can go from one to the other and hopefully provide more context for both. So what we'd like to do is now, if you'll recall, everything we've just done has been in one subject, specifically the first subject, right, that we fetched from the development data set. But for the machine learning analyses we're interested in doing in this example, you need a few subjects. So, I mean, if you want to do it well, you need a lot of subjects. But for the purposes of illustrating how it works, you only need a few, right? So this is not for research. This is just to show you kind of how it works. So what we'd like to do is classify, because I told you this data set had both children and adults, we'd like to classify when participants are watching the movie, were they a child or were they adult? And so what we're going to use to do that classification is we're going to learn based on their functional connectivity matrix as our feature of interest. And then the prediction, again, is which group they belong to. So one thing that's sort of fun is that we can really easily with Nilearn explore whether we're more or less accurate in our predictions based on how we define functional connectivity. So if you're familiar with this area, you'll know that there are lots and lots of ways that you can define functional connectivity. In this example, we'll think about 3. So we'll use correlation, which is perhaps the most common one. This is just pairwise correlation between every pair of possible ROIs, in this case, the 39 that are in the MSDL atlas. Partial correlation, which is pairwise correlation, but correcting for all the other correlations that are present. And then tangent space embedding, which uses a bit of both, actually. And what it really indexes is how, compared to the mean of all functional connectivity in the sample, how does a particular participant's pattern of functional connectivity differ from the group mean? So if you're interested in tangent space embedding, it's a bit less common. You can go ahead and I'd really recommend this paper because it does a really good job explaining what exactly it's doing. But here, for the purposes of illustration, it's just a third method to do functional connectivity, and it just provides another way to test and see, okay, how accurate can we be in learning?
Elizabeth, sorry to interrupt. I thought
No?
I thought this was just me, but someone else said in the chat there's a big blue block over the right side of your screen. I don't know if that's why that would be happening. Maybe try turning video on and off, or just stop sharing for a second.
Interesting.
Because it's blocking like most of the text on the right.
All right, let me try. How's that?
Yeah, perfect.
Cool. Sorry, I have no idea what happened there. This is the, the fun of technology. We're figuring it out. But thanks. Yeah. If anything else comes up, if you can't hear me, if you can't see something, please just shout out and let us know. Because that should not be the hard part of this, right? Okay, so what we'd like to do is we'd like to go ahead and do this classification example. So we're going to start, and this assumes that we're working in a completely new notebook. Just to kind of be rigorous, we'll go ahead and repaste it all in here, but this is stuff you've already seen. What this is really doing is it's doing the same imports as we did before, and then we're just making sure we have both of those data sets, so the first 30 subjects of fetch development, as well as the atlas we're using, defining that same nifty maps masker, again, because we have this probabilistic atlas. And then just to start off, we're going to set our correlation measure as the connectivity measure, as correlation, because again, this is perhaps the most common and the one that most people will be familiar with. Okay, so if you execute that, should be fine. It's just really everything we did before, but now condensed from a big block into one place. Okay, so now what we'd like to do is, whereas before what we were doing is we were doing everything just in that first participant, now we'd like to loop through all 30 participants and extract a few relevant pieces of information. So this is going to include their functional scan, their confounds file, because we just saw how important that was, and whether or not they were a child or an adult at the time of the scan, because this is the feature that we want to predict, right? So using this information, we're going to transform their data using the nifty maps masker we created above. And this is a really important question that someone brought up, and I answered in the chat, but I just want to also address live because I think it's a really, really conceptual idea, which is that one of the reasons that the nifty maps masker, we're not supplying confounds directly to it, is because what we're actually going to do is we're going to take this masker and we're going to apply it to every single participant. So we don't need to instantiate a different masker for every participant. We just have the one masker, and then we transform their data using that same masker. So this is nice because we don't need 30 maskers, or if you used all 155, you don't need 155 maskers. You just have the one, and then when you transform their data and their confounds, you can use the same information. Okay, perfect. So what we're going to do, again, I'm just going to copy this because I do want to be sensitive to time this time, but we will still walk through exactly what it's doing. So what we're doing is we're going to instantiate 3 lists. So first we're going to have this list called children. We're just going to collect kind of all of the children there, all the participants who were children at the time of the scan, so that we can look at them separately from the adults. We're also going to collect pooled subjects, which will be all of the subjects or participants, regardless of whether or not they were children or adults. And then we're also going to have this group information, which is going to tell us, for each of these 30 subjects, child or adult. Then we're going to loop through all 3 of these attributes. So the functional scans, the confounds, and the phenotypic file, which is basically just a list that we can iterate through. And that will give us kind of this triplet, which for every participant will be their functional file, their confound file, and their phenotypic information. And then we can go ahead and say, okay, using the masker that we've already defined, we're going to transform their functional file using their specific confounds. And then we're going to take that matrix, which is, you remember from last time, because remember it's n samples by n features. It's going to be 168 by 39. And we're going to append it to this time series object here. Oh no, sorry, I did the exact opposite. We're going to append time series, which we've created here. So the 168 by 39, we're going to append it to pooled subjects. So it doesn't matter if they were a child or adult, we're going to append that transformed matrix here. Then if we know from their phenotypic data that they were a child, we're also going to append their transformed time series specifically to children. And then, at the end, we'll go ahead and append to groups, whether or not they were a child or adult, because this is our feature that we'd like to predict. And then what we can do is, just to check in, we'll print out how many children are in this particular subset of 30 participants. And so that'll take a second to run, at least on my hub. So while it's running, I'm going to go ahead and switch to the book and just show you that there are 24 children. And actually, you may think that this is a lot of children for 30 total participants, and you're right. This is, quite a high proportion, right? So this is, even though this is a high proportion, the reason it is so high is because it was just this high in the original sample. So although the Nilearn fetcher is doing a pretty good job about keeping the proportions constant, in the original sample, which had, again, 155 people, there were 122 children and 33 adults. So we clearly don't have balanced groups here, and that's something we need to know when we go ahead and think about our classification later, because it's going to affect a lot of things, like how do we do a cross-validation, and what is our chance level, right? So this is just something that's really important to know, is that this is not a balanced sample, but it is proportional to what existed in the original data. Okay, this is still running for me, but that's fine. It's just gonna, here we go, perfect. Great, and you can see, at least on my hub, I'm getting exactly what we found before. And then just really quickly, I also want to check in, and just as I told you, right, so I said that here with this masker.transform, we were getting what we saw in the single subject case of 168 samples by 39 features for our 168 time points by our 39 ROIs. And you can confirm that that's true just by looking at one of the entries in pooled subjects. Let's just take the first one and then checking its shape. Oops, checking its shape. And if you could spell, which I cannot, you would see that that's exactly what you find, is that it's 168 by 39. Okay, cool. So a couple of questions that we can take really quickly. So one is, can the masker object account for anatomical differences between subjects? This is a great question. And I think this is something that confuses people a little bit. So Nilearn is not intended to do pre-processing, right? So something like fMRI prep or AFNI or FSL, which is worrying about things like making sure the anatomy is aligned to a standard space. That's something that Nilearn is not going to handle. So Nilearn can do a lot of things that are quite useful for pre-processing, like, you know, some steps we often think of as pre-processing, like smoothing, but it's really not a pre-processing library. It really assumes that your data has already been pre-processed and that all your subjects are already in a standard anatomical space. So if they are not, then you wouldn't be able to meet many of the assumptions that Nilearn has, and you get some kind of wonky results. So it can't account for anatomical differences between subjects if they're not in a standard space, but assuming you've pre-processed them and put them in some standard space already, then yes, it'll work within that standard space. Great question. Next question, how do you get a confounds attribute if you're not processing the data with fMRI prep? Great question. So I'm a big fan of fMRI prep. As you can tell, this whole data set uses fMRI prep in this example, but you definitely don't need fMRI prep for to be able to use this functionality, right? So all you need is a generated confounds file. So this could be generated, again, through any kind of software that does pre-processing. So if you really like AFNI, and AFNI is generated, for example, you know, the 6 motion parameters for you that you want, or maybe you want the derivatives, or however you'd like to use them, so long as they've been generated somewhere, you can still supply them to the masker using the confounds argument. So yeah, it doesn't need to be fMRI prep generated ones. It's just whatever software you've used that has generated confounds in some way. But it's a great question. Okay, cool. So what we have now is we have these lists, right, where we have all of these different matrices. And what we did last time was, when we did this, we didn't have a list, we only had one subject. But what we did for this one subject was we went ahead and created a correlation matrix just to see what it looked like. And indeed, you can do exactly the same thing here, but here we're actually going to do it for all of the subjects. So correlation measure, which again is just connectivity measure where I've set kind equal to correlation. It actually does quite well when we pass it this list of all the time series, the transform time series for the children. So here we can just pass it, and it will go ahead and create different correlation matrices, one for each child that was included in the list. So again, here we have 24 children, so it would be 24 correlation matrices. And you can check that just by seeing what the shape is, right? So here, I'm just going to copy paste it in again, but all I'm really doing is a print statement, which is saying what is the shape of correlation matrices. And it cut for some reason here. But anyway, it's 24 for the 24 children by 39 by 39. Because again, we have 39 ROIs. So we've gone across all 168 time points. And we just want to see those, because we're doing correlation, the pairwise correlations, which is 39 by 39 for the full matrix. Perfect. Okay. So this is pretty cool. This at least confirms what we're expecting. It's always nice to have these sorts of sanity checks. So the next thing we want to do is we could actually use this really handy attribute that's generated by this connectivity measure, this correlation measure called mean underscore. And what that is it gives us the mean correlation matrix. So this is one of the reasons it's really nice to do children separately is that we really expect that children and adults have different functional connectivity matrices. And if we have the children's connectivity matrices in one place, we can easily take the mean and then look at it across all of the children. So, oops. Yeah, I copied the right thing. So what this is doing is just saying the mean correlation matrix is this dot mean underscore. And then again, I'm just doing a longer version of taking the shape. And what you can see is it has a shape 39 by 39, which makes perfect sense because again, before we had 24 by 39 by 39, now we're just averaging across those 24. So this is pretty cool, but what does it look like, right? So first, let's just go ahead and display functional connectivity matrices of the first 3 children. So if I paste this in, you'll see the real difference from what we did last time is now I'm just using subplots. You may have seen these in a few different lectures now, but this just allows me to plot several figures next to one another. And then I'm going to go ahead and plot for each of the first 3 children their functional connectivity matrix using the same kind of plotting that I did before. And so I can see that one thing is different is that I didn't zero out the diagonal, but other than that, you can see that they really have, pretty unique structures for each of the matrices. So this is why it's really nice to see kind of what all the different participants look like. I can also, just as before, if you remember, we were able to generate that interactive view connectome plot. So I can do exactly the same thing, but rather than doing 3 of them, one for each of the first 3 children, or even 24 for all 24 children, I'm just going to plot the mean because that makes it a little bit easier to see kind of what the trends are here. Perfect. Okay, and now this shows me the mean connectome over all the children. Right, so this is pretty good. I think this is pretty cool. It gives us a little bit of insight into what exactly this data is looking like, again, while these children are watching a short Pixar film. So this is pretty cool. We have this, functional connectivity matrix defined by correlations, but I told you that we would think about a couple different ways to define functional connectivity because then we can use that in our machine learning analysis to see do different ways of defining functional connectivity differentially impact our accuracy in classifying participants as children or adults. So perhaps maybe the second most common kind of functional connectivity is partial correlation. And what's so nice is basically we can do exactly what we did above. The only difference is we're going to change this connectivity measure kind from correlation to partial correlation. Everything else stays the same, but we're able to really easily experiment and see, okay, what is the effect of doing partial correlation instead of full correlation? So here I've just gone ahead and fit that for all of the children. And then again, I'm just going to plot the first 3 just to see what it looks like, get a bit of an idea. And here you can see right away, it's a vastly different structure, right? So if I zoom back up, I can see that compared to just regular correlation, now it looks like there are many more weak correlations than before, and this makes a lot of sense, right? So if you're familiar with these, you know that with just correlation, we're looking at pairwise ROIs, but with partial correlation, we're correcting for other known connections. And so we therefore are trying to more directly investigate direct connections, and so we expect that there are fewer of those, right? So we can see this is a very different functional connectivity matrix, and we can then wonder about how will it impact our accuracy. But first, let's just go ahead and see what it looks like on the brain, because that's always fun. So if we do exactly what we did before, now the only difference is we have this partial correlation. We're still going to do the dot mean underscore. And we just go ahead and plot it on the brain. It'll take just a second. Here you go. And now you can see, just like we saw in the functional connectivity matrix, compared to full correlation, it looks like there are many, many fewer connections. So this makes sense. This aligns with what we would expect. And it's also just fun, right, to see it on the brain and see what it looks like. All right, the last kind that we're going to try to see how it impacts our accuracy when we get there is going to be tangent space embedding. So here, all we're going to do again, like just as before where we change kind to partial correlation, here we can change kind to tangent. And then we can fit again all 24 children's matrices using this tangent measure. And again, because I mentioned this maybe briefly in the beginning, if you're not familiar with tangent space embedding, the idea is that we want to see across the group how do the functional connectivity matrices look, and then we're going to model each individual as kind of a difference, or I call it here a perturbation from this group connectivity matrix. So what we're really looking at is variability, which means that we can't quite interpret it in the same way as we were doing before with things like negative correlations. But we can still look at it just to see what it looks like. And as you can see, yeah, like the diagonal no longer necessarily is one. So it's definitely something different here. And because of that, we also don't want to plot it on the brain. You could, but it would be set to 0, so you wouldn't see much. So it's just a good reminder that when you're doing these different kinds of functional connectivity, you need to differentially think about what you're really saying exists here, right? Like this is differently expressing the idea of a connectome in the brain. Okay, cool. So there are 2 quick questions that I think we can answer before we start, or a few quick questions that I think we can answer before we start the next section. So is there a robust measure for mean correlations? What if there are outliers? The first child's data seems to be quite different. Yeah, this is a great question. So one thing I'll note, because I noticed this in the tutorial as well, is that if by the first child's data, you mean the data we're using in the individual level case, that's actually an adult's data. So it is very impressive how different you can see are the differences between children and adults right away. So those definitely look very different. But in terms of, is there a robust measure for mean correlations? What if there are outliers? So the idea of what is the best measure for functional connectivity is kind of a long-standing one, right? It really depends on what you'd like to say or what you'd like to conclude from the data. So I think Gael, one of the reasons we have tangent space embedding in Nilearn is I think Gael would say tangent space embedding offers a really nice combination of properties. And we'll see a little bit later how it actually does in classification. But most people, when they're thinking about functional correlation or functional connectivity matrices, will think about correlation, right? That's just sort of the field norm. And so what you'd infer from a functional connectivity matrix defined by correlation versus what you'd infer from one defined by tangent space embedding are going to be very, very different. And so in terms of what's best, it's really going to depend on what kind of conclusions you want to draw from your data and what you want to be able to reasonably say. So it's hard to give an exact answer to that question in terms of which one is most appropriate. In terms of which is more robust, so things like partial correlation are going to correct, right, for the other correlations, which is really helpful if you want to hypothesize whether or not things are direct connections and make sure you're not just picking up on noise from co-occurring fluctuations that are maybe influenced by something else. But I think partial correlation hasn't seen as much uptake in the field, partially just because it's harder for people to interpret it. But the best way to do it is to kind of look at the data, see what it has, and think about what exactly you want to say about your connectivity matrices. Okay, there's another question, which is there a way to also control for global correlation, i.e. per subject average of correlation matrix? It's a great question. So we are not, in this particular example, doing global signal correction, right? So one thing you may notice is like fMRI prep does give you an estimate of the global signal. Many other software packages would give you an estimate of the global signal. And if you wanted to do traditional global signal correction, you could include that in your confounds that you pass to the masker, and then it would do kind of the traditional global signal correction for you. We're not going to do that here, but it's very, very easy to do. And so that would just be something about making sure you're selecting your confounds carefully in line with your research question. Absolutely. And you're specifically asking, it looks like, about controlling for per subject average of the correlation matrix. So you do, I'm not entirely sure I understand that question, only because the correlation matrix is already per subject, right? So you're going to get one correlation matrix per subject because it's over time. It's over those 168 time point samples. But if you're thinking about something like global signal correction, this idea of including the global signal in a confound that you would then correct for when you transform your data with the masker, that's probably the most logical place to do it, I would say. Right. And hopefully that answered all of your questions. There's one more question, which I will not answer because it is not the point of this tutorial, but it is a good question, which is, what is the impact of global signal on correlations? That is way outside of the scope of this tutorial. It's a very active research question. Everyone has their own opinions and different papers that they like to cite to point towards. But Nilearn can do whatever. Nilearn can either correct for it if you pass it to confounds, or it will not correct for it, as we did not when we did not pass it to confounds. So Nilearn is very agnostic to this question. But yes, it is a good question in the field. Okay, perfect. So cool. So now we have these 3 different kinds of connectivity matrices, functional connectivity matrices, that we've defined for all of our subjects. So right now we've only been showing the children, but if you remember from our for loop, we did it for all 30 subjects. So for the 24 children and for the 6 adults. So we have these 3 different kinds of connectivity matrices, and we'd like to see, can we use them in a classification analysis? So this is where we finally get to interface with scikit-learn, right? I've been telling you that Nilearn makes it so easy to interface with scikit-learn, and we can go ahead and do that, which is really nice because now our data is all set up to do it directly. So we're going to import a few different things from scikit-learn, and we're going to see that some of these may look familiar if you attended Tal's talk, or if you go to Gael's tomorrow, you'll also see some of these things as well. So we're going to have this accuracy score. We're going to have stratified shuffle split, which is really useful when we're thinking about cross-validation with unbalanced groups. Like I told you we have, right? We have 24 children out of 30 total participants in our case. And then we're also going to import this linear support vector classifier, which just means we're going to try and do a linear classification into whether or not participants were children or adults when they were scanned. Then we're just going to define a few things. So we're going to say the kinds of functional connectivity matrices we'd like to generate are correlation, partial correlation, and tangent, which we walked through before. We're then going to say how many classes do we have. So that's going to be, the groups that we've identified as children or adults. Our cross-validation, here abbreviated CB because it's much shorter. We're going to exactly use the stratified shuffle split. So that's going to make sure that our proportions of children and adults are appropriate given our unbalanced group size. So we'll have 15 different splits and a test size of 5. And then we're just going to take that pooled subjects. So if you remember, let me just scroll up because there've been a lot of things in between. So pooled subjects was this list where we were appending all of the time series, right, that we had transformed with the masker. We're just going to make that list into an array because it's a bit easier to work with arrays. That's really all. Okay, so I'm going to copy that in. And then now what we can do is we can actually just train the scikit-learn linear support vector classifier estimator on our training set of participants and apply the trained classifier on our testing set, storing accuracy scores across each cross-validation fold. So here we're just going to keep an index of the scores, and for each kind of functional connectivity measure, the 3 that we've identified, we're going to have a little dictionary where we store the different kind, and then we're going to go ahead and compute the accuracy. One thing to note that's a little bit different from what we've done so far is we're still going to use exactly this connectivity measure, and just as before, we're going to pass kind, but now we're going to supply this parameter vectorize. This is really, really useful because what it's going to do is instead of having this 39 by 39 matrix that's really lovely to visualize, it's not as useful directly for passing to machine learning models, because that 39 by 39 structure is really kind of for humans to see. What we'd like instead for the models is to turn that whole matrix into one long vector that we can use as our feature that we're predicting from. So this vectorize argument just goes ahead and does that conversion for you. So it's really pretty smooth. Then everything else is basically the same. So just as before, we fit the connectivity measure that we defined on the training set of subjects. And then we use those connectomes, those generated connectomes, to fit our linear classifier. And again, we're trying to predict the training set, or we're learning rather, excuse me, on the training set. And then we can predict for the test set, what do we think the classes are? And we generate the accuracy score by comparing the actual classes for the test set with the particular predictions that were made by the linear classifier. So I know this is a lot, but really I just want to say that the only bits that are new are here down, right? And this is just sklearn. So if you're familiar with sklearn, this is really, really nice because the only thing you needed to learn was these little bits of Nilearn. And now you can really easily go from a 4D fMRI time series directly to this classification model. And if you're more familiar with 4D fMRI time series, you can easily get from that to your machine learning model, which is really, really nice. It's quite smooth. So again, in the interest of time, I'm just gonna copy paste that. But hopefully it's pretty clear what it's doing. If you have any questions, just let me know. Okay, so it runs pretty quickly. So what we can do is go ahead and copy the next line, which is going to allow us to display the results, which is so exciting. All right, I'm just going to do it because it's really pretty cool. And then let's talk about what happened. All right, so here's what it looks like. So here we can see that we have this red dashed line at 0.8, which is our chance level, right? Because remember, we had 24 children out of 30 total participants. So if we were just guessing, if we were just following chance, we'd expect that if we always guess children, we'd be right 80% of the time, for example. So here we can go ahead and know that's chance. And now we want to compare everything to it. So we can see kind of the standard correlation is right around chance, partial correlation as well, but we see that tangent space embedding is actually performing better than chance. So it's more reliably distinguishing whether or not we're looking at children or adults. So this is really cool, right? So we can just look at these functional connectomes and we can do a full classification analysis, and depending on the kind of functional connectivity measure we use, we can more or less successfully classify whether or not participants were children or adults at the time that they viewed the movie, which is really quite nice. And if you wanted to see a little bit more about kind of what everything looked like, you could go to this scores dictionary that we set up, and you can actually see all the different values we got for our different cross-validation folds. So this provides a really nice kind of level of access to know exactly what happened at every point. So that's, I think, really, really cool. And I just want to emphasize, because we do have some time for questions, and I'd love to take questions, but I just want to emphasize this is really a small example to showcase Nilearn features. So this is not to say that tangent space embedding is, always going to be better in these kinds of situations. We really can't make that conclusion from 30 participants. But there have been some studies that have looked into this, and here I'm providing one that suggests that tangent space embedding is quite good. But that's really not the point of the notebook, although I think it's a nice, fun side conclusion. The point of the notebook is just to show that, if you have this research question in mind, how can I use classification in my fMRI or MRI analyses, then Nilearn, or not classification, but any scikit-learn model, any scikit-learn estimator, right? Nilearn makes it really, really easy to go from your MRI data through to a machine learning analysis. And we took a couple of detours just to look at various things that I think are really useful in doing that, right? Like understanding the masker objects a little bit better, understanding all the different kinds of data sets that you can access, and what you can do with each of them, as well as just plotting, seeing the data and seeing all the different formats of the data. So there's a lot in Nilearn that you can use to access these kinds of attributes, and there's even more that we haven't touched on yet. Like I mentioned, you could do smoothing. We did take the mean of an image. You could also do all kinds of other things that are really terribly useful. But this whole kind of process, it makes it really easy to go straight to machine learning models in all kinds of research applications. So if you're interested in learning more, again, I'd really, really point to the Nilearn website. I think it's phenomenal. There are a lot of really good examples and a lot of really good user guides kind of walking through some of this information, along with many, many different kinds of example analyses. So this is all something that's freely available online. And also very soon, hopefully, we just recently merged in the library NiStats, which I'm not gonna, didn't really talk about today, only because it's not yet in any officially released version of Nilearn. But eventually, when we make the next release, it will be in there, and that will allow you to do general linear modeling directly in Nilearn, which will really expand its functionality quite a lot. So that's something to look forward to. Okay, cool. So with that, let's take a few questions. Okay, I'm gonna now keep sharing, it's fine. All right, so one question is, how different would it be to predict continuous variables? This is a great question, right? So this has more to do with just machine learning analyses, like the different kinds of machine learning analyses. So if we wanted to predict a continuous variable, we wouldn't be doing classification, we would be doing a regression. And with a regression, there are lots of ways you can do that in scikit-learn, like ridge regression, for instance. In which case you would just make sure that the kind of data you're passing is relevant to that. So again, here you could imagine using the connectomes as your features that you're learning a particular target from, but the target would no longer be age group. It would probably, maybe the closest thing here would be something like age, chronological age. That would be a little bit difficult in this data set because the reason it lends itself to discrete age groups is because there's a bit of a gap. So the oldest child is 12, and I believe the youngest adult, if they're not 18, they're in their early 20s. So, you have a bit of a gap, and it's not too large of a sample, even with 155. Just because of the distribution of groups. But if you did have a sample where you could think about learning something like age, you would do a regression analysis. You could still, again, generate connectomes using different kinds of functional connectivity and pass those connectomes as predictors. But what you'd be predicting would be probably age or some other continuous valued feature of interest. Cool. All right. Yes, don't worry. I have not forgotten the question on structural MRI. So maybe one thing first to say is trying 3 measures seems to be an exploratory analysis. Is that considered acceptable for a publication? Great question. So this is really kind of a broader question than Nilearn, right? This is more like, what is appropriate when working with machine learning and neuroimaging data. There are lots and lots of caveats to think about here, right? So not only the different kinds of functional connectivity you use, but also things like, how would you do your cross-validation? you know, what was really, really popular and in neuroimaging still in some portions is still quite popular is to think about doing leave one out. But there's been a lot of good work showing that leave one out cross-validation is actually not something that we want to do, right? So the whole idea of machine learning and neuroimaging, there are a lot of kind of norms in the field that are still being worked out, a lot of best practices. I think Gael's talk tomorrow will really focus on a lot of those examples that he's seen in his career of kind of things to do and not to do. But I would just like to emphasize that this whole thing that we've done is not a research question, only because we have 30 subjects. The data that we're using is pretty aggressively downsampled, just so it's easier to work with, right? It's got a 4mm resolution, I think we downsampled it to. So I don't intend for what we did today to be seen as like a gold standard, take this and publish something just like it with your data. I don't think that's quite what this is, but what it is a really good example to see kind of how we can use Nilearn to do these sorts of analyses. Though, of course, if you wanted to do exactly an analysis like this in your publication, there's some things you'd want to change. So yeah, it's a great question. I'd just point you to kind of the broader question about how do we use machine learning and neuroimaging. And I'd be happy to talk about that more, but I do think if you're interested in that, I would definitely recommend Gael's lecture tomorrow. He's going to have a lot of thoughts based on his experience doing that. Okay, perfect. So which of these steps be different for structural MRI data? So this is a great question. Basically nothing that I've covered, right, was exactly geared towards structural MRI data, because what I was really thinking about was functional connectivity, which implies that you have functional MRI. But Nilearn does have tools to do structural MRI data. So for example, let's see how my internet is feeling. So yeah, so here you can see a really nice example about doing voxel-based morphometry on the OASIS data set. And I can paste this into the chat. Q&A chat. Here we go. Perfect. Okay, so if you're interested in using structural MRI data, there are different kinds of analyses that Nilearn is set up to allow you to do. So in this case, again, it's another aging example. This is sort of becoming a running theme. But here, what you're going to do is you're going to use the different gray matter and white matter maps and look to see, can you predict age? So here you'll notice a lot of the steps are quite similar. Not all of them. You're not going to do connectivity measure, but you do still have a nicety masker. You are still going to fit transform the data. You're going to still have shape. And then here you're doing a support vector regression, because again, you have this continuously valued age variable rather than a classification. So if you're trying to transfer this to structural data, I would say the basic outline is quite similar, but the particular tools that you'll use will again depend on your research question. Much in the same way, really, that the basic outline will be quite similar, but the particular tools you use will depend. For example, if you're not doing a binary classification, but you're doing, a support vector regression. The overall structure is the same. Nilearn is still very helpful to get you from point A to point B, but the particular pieces you would sub in to do so will be slightly different, just to match the kind of data you're using. But that's a great question. Hopefully that answers it, but please let me know if not. Okay. There's another question, which is, there are many kinds of neuroimaging data that are not captured from the human brain, or if they're human, are captured from tissue section. Can Nilearn analyze any of these other data types, or are there other modules that are available? This is a great question too, right? So this is something that's kind of floated around for some time. There have been different groups that are interested in using Nilearn to look at, for example, mouse recordings and macaque recordings. I think there's a lot of really good work that's happened in that area, but that work hasn't actually flowed into Nilearn, partially, well, almost entirely because of sort of a scoping issue, right? Like there's so many different kinds of data that you could imagine going into Nilearn, and Nilearn just doesn't, like it's not helpful if it balloons so much that the maintainers no longer know exactly what they're working with. So instead, what's ended up happening is there have been a couple of developers. Horea Christensen actually is one that comes to mind, who've come and kind of showed stuff they're working on in Nilearn and provided some links for it. I can definitely get those for you. I may not subject everyone to me looking through Nilearn's GitHub history right now. But I know exactly where they are on Nilearn GitHub. And so what I would say is, like, if you're interested in using Nilearn-esque software to look at non-human animal recordings, or rather MRI, then ping me in that main Slack channel for this lesson, and I will grab you the links for a couple places where other software that has a similar sort of setup has been recommended. But that's not something that Nilearn itself is doing directly, and I don't think it will be, actually. I think Nilearn is pretty strongly going to stay just to humans, and really not even to tissue samples at this point. Okay, and then the other thing is, can you recover the original data shape after you've vectorized if you want to explore edge coefficients that informed the classification? Ah, yes. Okay. So after when you vectorized a connectivity matrix, can you go back to the unvectorized form and look at what edges informed the classification? So that's a really good question. That's something a lot of people are interested in. So yes, you can go back. I'm kind of blanking at the moment on the particular command, but that is also something I can grab for you. But I would caution, there's been a lot of really good research. So Nilearn is quite nice for this, right? In kind of like going back and forth between the two. So I can even share an example where we see, like, looking at the particular weights that were used in a classification on the brain. One thing to know is that you just want to be really careful when you're interpreting weight images, just generally, right? So if you're looking at what edges or what voxels or, you know, what features in your brain really contributed to a classification, it's not necessarily clear that they contributed for the reason you're thinking. It could be because of something like head motion, right? So you just want to be careful when you're interpreting it, but it is absolutely possible to access it. Yeah, absolutely. And I can pull up, again, I don't know that I want to subject people to me going through the user guide, but I can definitely pull up another example on that as well. That's a great question. Perfect. Okay. I'm not sure if there are any other questions, or if we can actually have a little bit of a break before the next session, because I know today is sort of a long day, so that might be the best thing to do. What do you think, Tal? If I don't hear from
it's up to you, I think. I mean, a break is fine. Certainly, there's no reason to force it if there's no more questions. And yeah, we didn't, unfortunately, we have no actual lunch break because there was just too much good stuff to fit into the schedule. But obviously, you know, people should, we can't see anyone, so you're welcome to walk around and eat at your desk or on the couch. So it's up to you.
Yeah, no. So why don't we, okay, yeah, there's one more question, and that sounds great. I will answer this question. If people think of more questions in the meantime, please add them in. And I'm really happy to keep talking until the hour. I can always find things to talk about with Nilearn. But yeah, if people want to hop off and grab lunch or something else, that sounds great too. Okay, so can I describe a little bit more about the NiStats integration? Great question. So NiStats is this really, really cool project that was started a couple of years ago. And the idea, I think even in the beginning, the idea was that it would eventually merge into Nilearn. But it provides a nice way to do things like fitting a first and second level general linear model, even from, say, a BIDS data set. And so what has ended up happening is we merged it into the main Nilearn code base, a couple months ago now. And we're kind of working out a few differences that crept up between the libraries just when they were developed separately. So there are a few more things that we need to smooth out to make sure that, you know, if you're calling Nilearn.stats is going to be the new name. So if you're calling something from Nilearn.stats versus something from like Nilearn.image, that they have about the same kind of structure and that they'd expect about the same kind of arguments. So that's still something that we're actively working on. But once that is done, then you should see a new Nilearn release. And in the new Nilearn release, you'll be able to access all of the NiStats functionality under Nilearn.stats. So that's really, really exciting. I think right now, all of the Nilearn developers really want that to happen. We're just, at the moment, we're totally a volunteer-based team. And so it's a little bit hard to make sure that that's moving forward as quickly as we'd like. But maybe this is a good opportunity to advertise that if you really love Nilearn and you really love software development, Bertrand Therian, who's one of the lead PIs on the project, is actually actively recruiting a Nilearn developer. So if you'd like to live in Paris and work on Nilearn, that is definitely the job posting for you. And you could do lots of fun things like work on NiStats integration and all other kind of cool features to make it really, really easy for us neuroimagers to go ahead and work with these machine learning analyses. So I hope that we'll see the NiStats integration released very soon. But if you want to kind of trial out the very alpha version, it's currently in the master branch on Nilearn. So it is there to play around with, and if you'd love to contribute and help make it better, I think that would be fantastic. But great question.
All right, well, I guess unless there's any other questions in the next 20 seconds, I think this is probably a good time to stop. Thanks for that. That was fantastic, Elizabeth.
Thank you. Yeah, no, and I know I owe at least 2 people resources, so expect those in the Slack channel. I'll paste those there. And if any other questions come up at any point, please just add them in there as well. I'm happy to chat about it. And I'm also always on the Nilearn GitHub, so you can always open issues there, and we're all there as well.
Awesome. Thank you so much. All right. See you all in a bit in a different chat room.